Do something. Welcome. Thanks for making the long way to this talk. I appreciate you all being here. I also know that if there's a talk happening, you're working there, it's hard not to go to the talk because it's awkward. So if anyone wants to do something completely different, I will not judge you. And that's fine. But for all that care, I'm going to try to introduce you to CockroachDB. I'm going to talk a little bit about what that actually is. And more than anything about how we built the system and why we built the system that way. And kind of cater to that schooling aspect. There's also going to be some more general stuff that is not directly about CockroachDB, but that kind of puts into perspective what we do in CockroachDB. So hopefully that should be interesting. And to start off, let's talk about what we actually want from a database. Like I'm not yet sure what you guys are running here, but I will definitely try to find out before I leave this building. But essentially, a lot of companies, they want something that's scalable, should grow to any size. If you have more data, it's fine. Just throw another node in here. It should be transparent to apps. You don't want to have to like reconfigure everything and do weird stuff. And operationally, you want this thing to be a breeze, right? It shouldn't page you in the middle of the night. Shouldn't have those 1,000 dashboards that nobody except this one person on the team can read. Should be kind of easy to handle. Should also be survivable. Like if there's a problem and it's actually a serious one, like data center catches on fire, Trump gets elected, and electricity gets shut down in parts of the country, who knows? Then the database should kind of do its best to still be there. So typically what that means is that you want data to be replicated. You want to have more than one copy of the things you hold dear, which makes a lot of sense. In practice, that would mean either some kind of local replication, so replicate with small latencies, but also maybe you're replicating between different data centers all across the continent or even across the world. And when things go wrong and the cluster is still alive, because it's great, you still wanted to kind of figure out how to get to exactly very good state again. So it should kind of figure out how to repair itself, maybe create new copies of data if one source of the data was lost. So that's also something ideally that you would want. And the other thing is we think you really want is strong consistency, and that is in juxtaposition to eventual consistency. Eventual consistency meaning, well, you have one primary copy and you want to have more copies, but you're really not willing to make that synchronous. You're kind of just doing it best effort in the background. And if things go wrong, then maybe the client sees inconsistent data at some point. And in practice, especially if you really want the data to be congruent, that means a lot of work put in on the side of the application developer, or even worse, that work not being put in, which means that everything looks fine until something goes wrong, in which case everything goes pretty wrong. In any case, having strong consistency removes a lot of work and care that you need to put into application design and lets application developers do what they actually want, which is just use a database and expect it to work intuitively. And well, whether you like it or not, SQL is kind of the standard at this point. It's got decades of, well, different versions and extensions, but also decades of production usage. It's simply a proven platform. So we think eventually you're going to want something like SQL, especially if you're looking to migrate in from another system. A lot of databases that don't strictly support SQL, they've kind of converged to supporting something like SQL. There are a few others out there that have a different concept, which are also seeing usage. But as a whole, especially if you're also talking about analytics and kind of a multi-purpose platform, which is used by a lot of different projects, I think SQL is the way to go. And ideally, that SQL would also be scale out. So you would, if you picture like a huge data set and you run an aggregate over that huge data set, in the background, that should somehow be sharded and some of the work delegated to parts of the system that actually hold the data. You don't want to just stream the whole thing to your client and let the filtering happen there. So you want to do this in kind of a way that makes use of the size of your cluster. And when you're talking about SQL, one of the major pain points often are migrations. So you're adding a column, you want a new index. If that is something that could potentially block your system for a day, if you have terabytes and terabytes of data, not good. So you want something that actually thought about this before it happened and has something like online schema changes. And that's a pretty good summary of what we're trying to do with CockroachDB. Of course, we have a flashy mission, which is make data easy. And that basically does what I told you about before, and now the rest of the talk is going to try to explain how we get that and which kind of design decisions went into this. The good thing about Cockroach is it's also open source, which is really nice for us who are working on it, because like, everything's online. If we try to get hired somewhere else, well, good resume. No, but on a bigger scale, like it's a database. It's kind of the heart of the operation in many places. So it really gives me personally a lot of comfort knowing that all the world can potentially look at that code and find out issues and report them freely without, I don't know, some kind of proprietary barrier in between. So the open source aspect seems minimal, but it's actually one of the driving forces behind the project from the very get-go. Like, it was never a closed source project. It was never considered to be a closed source project. It was in GitHub essentially from day one. Not even essentially, it was on GitHub from day one. All right, so mission, make data easy. Now you could say, well, isn't data already pretty easy? Like, why another database? Like, there are already 100 to choose from. But for kind of the general purpose database, we're mostly talking about OLTP workloads at the moment. Like, we're thinking about analytics, but not too hard at the moment. So think like small transactions that actually need consistency. Like, why another one? And we posit that with the existing ecosystem out there, you really don't have that sweet spot that you want. Like, you can either go like full on standard SQL, like you use Postgres, MySQL, Oracle, if you throw a lot of money at it. You're still going to have problems with scale. You're going to have problems with fault tolerance. We're going to like see like how primary, secondary replication works in trivial case later. If you go more towards the NoSQL side, say you just use Cassandra, transactions are kind of iffy, and you might need them one day. It could be tricky. Indexes, especially secondary indexes, are pretty tricky on Cassandra. And of course, you're always going to have kind of consistency issues, which come from the underlying design choice of leaning towards eventual consistency as opposed to synchronous replication. So that is to set the stage. And the following points outline kind of the aspects that we're going to cover today, and that will talk mostly about CockroachDB, but also put into context in a more general context. So we're going to talk about the high-level architecture, so what's actually in that system, like what moving parts do they have, and what are the abstractions that we operate on. Then we're going to talk a lot about distributing data. Roughly, that means I have a lot of data. It's not on one machine, so it's on many machines. How do I figure out which data goes where, and how do I find the data that I'm looking for, which is not a trivial problem. Then we're going to talk about replication and transactions. So I want multiple copies of my data in case one rack catches on fire. How do I do this without veering into the eventual consistency territory? And that kind of leads us over to talking about transactions, which is how do I mutate different things in an ACID compliant manner? So how do I make many things happen at once or not at all in a way that makes it seem like I'm just doing everything at the same time? And of course, we're going to talk about SQL, this being a SQL database. And mostly we're going to talk about how SQL actually translates to the underlying data store, which hopefully gives you a pretty good idea that there's no magic going on. It's just a series of abstractions, each using the next level. And then there's a brief deployment section at the end, because the members of the team have gone through many deployment pains at previous jobs. And so we have put considerable amount of work in there at Cockroach, and so I want to just show you how that works. All right. Oh yeah, and feel free to use that Google Slides link to ask questions. I know I usually talk fast, but I like questions, so it'd be cool to get some. So let's start with architecture. So this is the bird's eye view, and that comes in two confusing text boxes. Let's go from the top. Like if you're talking to a Cockroach node, you're going to be talking essentially in the same way as you're talking to a Postgres server. So for a moment, you think you have this big cluster of Cockroach nodes. If you just talk to any of them and you just use standard PostgreSQL, that is how you talk to Cockroach. So it's fairly easy. So you talk the Postgres wire protocol, which is SQL. And internally, that SQL gets translated into operations on a transactional key value store. So what is that thing? A key value store is simply a database that stores keys and values, and that allows you to put a value into a key and to get a value from a key, and then maybe some range operations. What does the word transactional mean? It means that you not only can get and put data, but you can start a transaction and get and put data in that transaction and then commit that thing, and it will make sure that everything happens at once and that you don't conflict in weird ways with other overlapping clients manipulating the same data. So that's the transactional part. The way that this is implemented is as a monolithic sorted map. So think again like a key value store, but the interesting thing is that the keys are ordered. So you can actually scan from A to B, which is not the case if you're thinking of, for instance, a hash map. And this monolithic map, in turn, already does the replication for you on a lower level. So if you put something into that map and it comes back as a success, you have not only written one copy of the data, you've already written the copies of the data that you wanted. So if that one node that has the data dies, there's still another one out there that has it. And we're going to talk about this in detail as well. So that's kind of the logical abstraction. If we're talking about the physical storage, then you have the node, which would correspond to one running process of Cockroach. So it could be a server in your rack. It could be a Docker container. It could be a physical VM in your basement. Each node has a number of stores, and a store is really just a storage medium that you've dedicated to Cockroach. So it would be an SSD or a spinning disk, or maybe if you kind of have a weird use case, it could also be a RAM disk, but that's probably not going to happen. So each store is a hard drive, essentially. And now we're coming to the more interesting part, which is the range. So I already explained that the data that we store is essentially a sorted map of key and values. And the range is the unit at which we shard. So each range aims to hold about 64 megabytes of sorted key value pairs. And we're going to see ranges a lot. Yeah, we're going to see them a lot. So hopefully that will be filled with intuitive meaning in just a second. All right. That's already it for architecture, but we're going to revisit these individual parts in just a second. So let's talk about the monolithic map for a second, which is the part that distributes data. And before we talk specifically about Cockroach, let's talk generally. Like, if you have a lot of data and you want to store it on a number of nodes, you have two key questions, the first one being the more prominent one, I think. So you have all this data in your cluster, but if I want this key A, like how do I actually figure out where in the cluster it is? And you have really two big options of going about this. One, you can either do something hashing, something that uses hashing, or you can do something order preserving. And I'll explain both of these. Hashing first, and I want to point out this is not what we do. It's close to what Cassandra does in the standard configuration. And so what you do there is you just say, oh, I'm just going to use a hash function. I have like n nodes, and we're just going to use a hash function that randomly assigns keys to these nodes. So what I do to find the nodes, I'm just going to compute my hash function of that shard key. I'm getting a number back, or even IP, depending on how it's set up. So that is a node I'm going to talk to, and then I go and talk to it, and it has the data, and I'm happy. And implicitly, that means that I have an index that maps keys to a shard, but it's implicitly represented to through a function, which is kind of cool because there is no data structure that you're kind of holding in memory. It's very simple to find the shard. But one thing that's kind of bad is that range scans are pretty awkward. So because a hash function gives you random outputs for your inputs, keys that might be very close together in the hash function would be shot all over the place. And as a kind of pictogram to this, just consider like you have a bunch of fruit and you have this hash function which distributes the data over 3 nodes. So they're pretty much randomized here, right? So node 1 has apricot and raspberry, which are not very close in the alphabet. Number 2 has banana, which you would expect that to be close to apricot. So it's essentially random. So now if you want a range scan, you want everything between cherry and mango. There's really not much you can do except for going to all the shards, asking them for all their fruits that are in that range, and then collecting them, and then you even have to order them when they come back. So it's not that great. And in this picture, it looks kind of reasonable because you touch every shard, but there's also a result on every shard. So you need to do that anyway. But if you have 100 shards, you don't want to go to 100 shards. You want to go to a very bounded number of shards that you actually know could possibly hold something that you're interested in. So that is kind of one problem. And another problem is resharding is a headache, right? You have a function that maps all your shards. What if you have a new shard? Now you need to change that function so that it actually knows about that new shard. If you go about this trivially, that's pretty horrible because right, every randomly chosen place will be another randomly chosen place, so everything has to move essentially. That is not what anyone does in practice. You use something called consistent hashing, but even then, in this example, 1/4 of your keys will just have to find a new home. And they're kind of all over the place. It's kind of awkward. And the other big option, and this is actually what CockroachDB does, it's also what Bigtable does, it's also what HBase does, and it's also what Spanner does, is you do something order preserving. So your shards are actually ordered parts of the key space, which has an immediate upside, which is that you can actually efficiently range scan because, well, everything is already sorted, and so there's no guesswork involved. But what you need to do is you don't have this simple hash function to look up the shards anymore, so now you need an additional way, given a piece of data, to figure out where that corresponding shard is. So you have more indexing structure that you need to keep. And what would that look like? Well, on the lowest level, of course, you would have the shards, and now each shard is not just some number that gets hit by a hash function. Now it actually has a key range associated to it. So here we have 3, and they carry the corresponding keys, and you'll see that they're sorted. Well, they're actually not sorted, but that's because the slide mixed. No, they're sorted. Perfect. All right. But now you need to actually find the shard, so you have another shard index, which you also have to figure out where does that live. But anyway, you have this shard index. And so if you want to find a key, you go to that shard index. It tells you which shard contains that key range or that key, and then you go down there. So if you do a range scan, it'll be easier because cherry and mango, you look at the shard index, you know it can only be in one of the first two shards, and that's where you go. So you don't even query the third shard. And of course, in practice, there's not only one shard you don't query, there are probably hundreds. Cool. And the other thing you can do, or the other thing that's problematic, even if you have something like that, like you have predefined boundaries at which the shards live. But what if suddenly all of the new fruits that come in for the next eternity, they all go to PEA to infinity? Like that last shard, it would just grow and grow and grow and grow and grow, and you're very uncomfortable with this because you want your shards to be approximately the same size. That was the whole idea, that you would split your big data into smaller data. Well, you need to be able to change that indexing structure, obviously. So you would make a new shard which takes part of the old shard, so you move part of the data somewhere else, and you need to update that indexing structure. And that might look really easy on the picture, but in practice, of course, what you kind of want to do is you want to adapt that shard index, which is somewhere in your distributed system, and you want to adapt the actual data location. You want to do that atomically, at least as atomically as you can, or at least in a way that doesn't change the index first, and then you try to move the data, but some client has already tried to read it, but it's not there yet. So you can kind of see that you have some atomicity problems here that you need to solve. So it is tricky to get that right, but it is really nice because you can just split charts when they get too big, and you can also split based on other criteria. If you have a range that gets a lot of write pressure, you may want to split that range even though it's not so big, just so that the nodes that are involved are not all the same node. Okay, so we like order preserving, which means we have this additional indexing structure. And yeah, this is pretty complex. It's not going to show up in the talk much, but you can ask about this at any time, and maybe I'll ask you where you think that lives later. All right, so this idea is, well, not very new. Bigtable has it. It's called a tablet. HBase has it. It's called a region. For variety, we call it a range. I don't know why we chose a third name. And what I hinted at the beginning is that it also matters like kind of what your unit of distribution is. Like you could say, well, my shard is simply everything. So you have one huge shard, which is kind of bad because if you want to move that shard somewhere else, you suddenly have to move all of your data. There's not a lot of granularity. On the other hand, if you have very, very small shards, you're going to be like they're going to be too big all the time. You want to move them, split them all the time. Your index is going to be huge because you have so many shards. So there's a lot of overhead there. So what you want are shards or ranges which are big enough to usually satisfy the queries that you run, but they should also be small enough to be moved around quickly. And currently what we do is about 64 megabytes of data, which is kind of precedence. Well, Cassandra has a little bit bigger shards, but internally at Google, like 64 megabytes is something that's been floating around a lot. Okay, so roughly speaking, Cockroach shards on a 64 megabyte level has an additional indexing structure, so you can actually find those shards, and does a lot of the heavy work, a lot of the tricky work for you that you can use to automatically reshard. And if you have a two-node system, ignoring replication, so only one copy of the data, it's going to look a little bit like this. You have your shards on one node, you have some other shards on node 2, and somewhere, not in the picture, is this indexing structure that you would actually use to figure out which node to talk to for which piece of data. And if you close your eyes a lot, it looks a little bit like a B tree. And in fact, like the B tree pops up everywhere. So to recap, we want order preservation, so we have this high-level index. We have a modest range size to allow auto rebalancing and repair. And this index structure is kind of more complex than hashing, but it allows a lot of flexibility in data placement, especially to avoid hotspots. OK. I'm not seeing a question, so I'm going to slowly continue. So let's go to the very bottom layer. We haven't talked about replication at all. Like in those pictures when I talked about charting, there was only ever one copy. But that is not what we actually do. And in practice, it's also not what anyone wants, except if you don't. Yes? I can ask a question. Oh, you did? Really? Oh, I'm gonna catch up. Yeah. So I'm Ron Burgundy, OK. I'm going to upvote that one. Oh, I can't upvote my own questions? That's a bummer. LaTeX support is bad. Hey, why not? Oh, what's the why not for?
Oh, yeah, so
can I
say a little bit more about why I wouldn't want to read from lots of things at the same time?
Come again?
A lot of times I can use more network that way. wasn't totally clear to me that off the bat I want to chunk this.
Sorry, you can.
Why do I want to always chunk the reads onto as few nodes as possible?
Oh, this is mostly like if you're using SQL, you're always essentially wanting to use indexes, and indexes are inherently sorted data structure. So a lot of times you actually do want that. If you're thinking of a case where you have like a huge table and you have a lot of random reads and you don't want them to hotspot, yeah, that's easy too. You just have to figure out a primary key that actually randomizes them, right? You shouldn't. Then if you don't want that, then you just don't store them in sorted order. But you have the choice, right? It's not like you're getting forced to do that. But yeah, there are a lot of workloads in which you actually want to have things decentralized. Also, they're also like, yeah, we can talk about this more after. But essentially, if you want the things to go all over the place, you can just put in a hash yourself, like have a random primary key. It's essentially what happens if you, in Cockroach, if you create a table that doesn't have a primary key, it will give you a hidden randomized one, essentially. So that will have the behavior that you wanted. Yeah, but you can also do it yourself. OK, so that is number one. Why not read from many shards at once? Oh, I see. OK, yeah, there's a trade-off. Like if you're going in for one read, like you save a lot of round trips if you simply hit one shard and has everything that you want. If you're doing more analytics-like things, then obviously you want to do a lot in parallel. And this is also something that we're working on. Like we're building a distributed SQL framework, which would actually, if you're running like a full table scan and compute something, it would actually go and designate like parts of that work to the nodes that actually have the data, and they would pre-aggregate, and then they would kind of fan in back to your coordinator and do all this complicated stuff. Yeah, that's also something that we're building, but not right now. Right now, it's going to be stupid and basically pull the whole table into that node that you're talking to, like one chunk at a time, filter it. So it's going to be sequential.
So I think one example is just kind of like our training. We want to pull 1 million examples from that table. So it's kind of a cursor sequential rate. We don't want data distributing all over the cluster. So there's a lot of random seed, a lot of places. So if all of data sitting in one place, you just break a big chunk of data and keep breaking.
Yep. What if you have multiple columns you want to range by? What is the, who asked that?
Me.
Okay.
Yeah, so like in your example, you were sorting by apple, but like let's say you want to sort by apple or sort by like fruit size.
Mm-hmm.
Is your schema, how do you shardify that?
Well, maybe that's going to be more clear once I actually talk about how SQL maps down to KV. But essentially, what you always have is an index, right? So if you want to have two things that you're sorting by, then presumably one of these would be a primary index, and you would have a secondary index, which is sorted on the other side. Yeah. So it's like, and optimizing for locality of those things is kind of very tricky. But essentially, yeah, you would have another index. And I think it's also if you have big secondary indexes, it's also, I think, still the best practice in Cassandra, which is really bad about its secondary indexes. In Cockroach, you don't have that problem because it's not a uncommon use case to have like two indexes. Except that if they're in different parts of the system, each write actually has to update both of them. So if you're not careful about how you do this, then you might catch like bad latencies and your writes get slower. So this being like a distributed system, there's a lot of tricky stuff, but hopefully that is manageable. At least we know from Google, who has Spanner, which does something very close to what we're trying to do. We know it. You can kind of figure it out. It just takes a lot of work. Yeah. All right. Can the user change his 64 megabyte range size? Yes, they can. There's something we call a zone config. So essentially, this being a sorted key value store, the configuration is set on a key prefix. So you could have one database, SQL database, which would correspond to one key prefix. And you could give that a certain configuration. So you could say ranges must be at least 16 megs, and they can be up to 128 megs. And so once the range stays in that area, it will not be changed. So it's configurable by entity group, essentially. And along with this, you can also configure where that data actually lives. So if you have data centers here in Shanghai, you can force some part of the data to live here. You can force other data to live in Shanghai. You can force it to have one copy here, one in Shanghai. So this is all configurable. Did that answer the question? Yeah, perfect. Do you reshard as your schema involved, or are you locked into how the data is structured from the start? That is Trey again, right? Yeah. So by schema, you mean the SQL schema, right? So I would add a column.
Or like add a new index or
Uh-huh.
index?
Well, the sharding really happens based on the key, right? It's not the SQL layer is it kind of needs to know about where the data lives because it wants to make the access efficient, but it doesn't try to control where things go. So if you create, for instance, a new index, that new index will have a certain key prefix, and that dictates where the data goes. So it'll just blindly start writing. It will write, and the underlying system will actually see if the data if the ranges get too big, and will split them and possibly move them around. We're going to have to think about how much interaction there should be, especially if you're talking about locality. Like there are things which often get accessed in the same transaction. You don't want to send like them all over the place because you then have a lot of random RPCs. But essentially, and at the moment, the SQL layer is completely oblivious to all that. It's encapsulated away in a lower level. Yeah. All right. I'm caught up. Cool. Thanks. It's fun to have a lot of questions. OK, where are we at? Yes, replication and consensus. Going from that one dangerously isolated copy to more than one. And just a really quick recap, like if you're in a company that's not really up to speed with current technology, maybe locked into that database that they started 15 years ago, what you're likely going to see is that they do something like primary, secondary replication. Again, disclaimer, this is not what we do. It'd be kind of insane at this point. But essentially the idea, and I'm sure all of you know this, is that instead of one database server, you have two. And when you write to one, you also write to the second. So it's problem solved. You have two identical copies of the data. All right. Yeah, of course, it's not that easy. You have to figure out your trade-offs. You can do asynchronous versus asynchronous, and that means a trade-off between consistency and latency. So the one thing you can do is to do it asynchronously. So when a write comes in on the primary, you acknowledge that immediately to the client when you've written it locally, and then you kind of go and try to give it to the other guy, hoping that he'll get it. That, of course, means that if something goes bad before you manage to tell the other guy about it, then, well, you don't really know what state you're at. So there's a lot of bin log stuff involved, and it's, yeah, kind of tricky sometimes. But essentially, that's what you try to do. You could also do this synchronously if you want a little bit more security. So you would not immediately acknowledge the stuff that you got to the client after you've applied it locally. You would also send it to the secondary, wait till the secondary actually has it, and then you go back to the client. The problem with this is those things really don't matter unless something goes wrong. And you kind of need a third party to figure out when something goes wrong. Like if the primary and the secondary are still both running, but somehow the primary doesn't work, it deteriorates. Like when do you switch to the secondary? How do you figure out if there's a write that made it to the primary but hasn't been replicated? All of those problems, you end up like re-implementing kind of hacky, like band-aid solutions about them that you don't really want to test in practice. So this stuff looks innocuous, but this is really hard to get right. And we're definitely not chancing it, leaving that to anyone who runs a database. It should be an integral part of the design, and that's what we do. And the way that usually all systems that do this go about this is consensus replication. So they do something that's way more involved, but also gives you a good feeling when you go to bed at night. So they replicate. Instead of having just a primary and a secondary, usually you have a group of 3 nodes that are supposed to have copies of that data. And a piece of data is only acknowledged when it's written on a majority. And it's written not only randomly into the store, it's written into an operation log so that when a node goes down and a new node turns up to be the primary, it actually is guaranteed to not lose any of the data that has been committed before. And this is like what all the cool kids do, like Aurora does it, Spanner does it, etc does it, and of course CockroachDB does it too. And the way that works in practice is you have one leader, which is elected by the consensus protocol, which is in charge of serving reads and writes. There are a lot of variations on this, but essentially, let's say that everyone is trying to talk to the leader. And now you write cherry into that node. It's going to put it into an operation log, and it's going to try to replicate it to its followers. So it tries to talk to both of them. Says them, hey, I got this command. You want to apply that to your log? And once the first node, one of the 2 nodes, comes back to the leader knows at that point that's at least in 2 operations log out of 3. So that's enough to make it committed and acknowledges to the client. And the reason why that's better than just having 2 nodes which kind of try best effort to get it right is that if you try that right on the leader and now there's a problem, the leader starts burning, it crashes, I don't know. In any case, it's not really there anymore. It's a follower, may not even be participating. A new leader which is selected, which doesn't have that right, doesn't have to have that right because it was never on a majority. If it had made it on a majority, that guy who doesn't have it couldn't be the leader. The leader always has to have the data that has been on a majority. That's guaranteed by the consensus protocol. So for all intents and purposes, in that situation, that partially written key, which hasn't made it on a majority, does not exist. And will actually, in that consensus protocol that we're using, will actually be discarded from the log, which is fine because it's never been committed, it's never been acknowledged to the client. It's just like a single write to a database which failed. All right, and this preceding explanation is definitely the airplane version on a very small screen, so a lot of detail was omitted. Consensus is has been actively researched for a couple of decades. But the essential takeaway is that consensus provides kind of an atomic primitive for replication. So you do something, and the consensus algorithm tells you either that it succeeded or it hasn't succeeded. So it's never half there. So you don't have these eventual consistency type of situations. And we're going to use that as a building block for higher levels of the system. And for those who are curious, we're using Raft, which is also what etsy uses. It's a relatively recent algorithm, which is kind of close to Paxos, but we think a little bit less hard to implement, even though in reality it's still pretty fucking hard, especially if you're looking at membership changes. So you have 3 replicas, and now you have this new, you want to change your group size to 4. So how do you, what is the quorum there while that happens? It's all very tricky. And then you have to synchronize that to the actual data you have on disk. There's a lot of work that goes into that. But the good thing is, this is the actual work that you would have to do otherwise if you try to do it yourself, and it's really hard to get wrong. All right, it's really easy to get wrong. OK, that is about replication. And to have a nice picture, in practice, remember the key ranges are the sorted bits of key space. They would be replicated threefold and kind of talk among each other using the Raft consensus protocol. And they're all located usually on 3 nodes, even though you can totally configure that. You could have 5, you could have 7. I don't think anyone does that in practice because there's a limit to how much safety you want. And now maybe, let's see if I have anything here. Nope, perfect. So as a question to the class, I talked about this weird indexing structure, right? To basically, if I want to write key A, I know there's a range on 3 nodes which has that key, but how do I figure out which one it is? There's this indexing structure that tells me this. Where do you think we store that? Right, that's one way to do it. We could just run an etsy, another object on the side that actually gives us that information. But we kind of we really don't want a dependency on another system. And the answer to that is we store it in those ranges itself. And now if you think about this, is kind of really creepy. How does this work? We want to find a range, but we store that location maybe in that range that we're trying to find. So there's a lot of complexity here, and the slides don't mention this at all. But I at least want to point it out because it's a pretty important part on how this whole indexing bootstrapping works. So what we do in practice is there is a separate system which is integrated into Cockroach, and it's essentially a discovery network. It's a gossip network. So when a node joins a cluster, it needs to know about some other node, at least, to be able to figure out where everyone is. And they kind of join a peer-to-peer network and talk among each other, and they exchange some information. And one of the bits of information that they exchange is actually the address of the node that holds the first range. So it's the range which sits at the very beginning of the key space. So it's the empty key to something. And then by convention, we require that this very first range holds the beginning of this indexing structure. And so that means without knowing anything about the ranges, just from this gossip network, you can get that location of the first range. So you can talk to that first range. And that is enough to bootstrap all the rest. And because the system is supposed to scale, this indexing structure is actually 2 levels. So the first range has the locations of all the nodes that have information for the second level of that indexing. So you might go to the first range that gives you a lot of locations, and you go to the second range, and then that guy actually has the location of the key that you're looking for. So it's pretty complicated, but even worse, as ranges split and data moves around, you want to update this thing kind of atomically with the actual movement of the data. So you want to update this in a transaction, which in turn needs to look up locations, and it's very convoluted. But what it comes down to, there's one situation in which you actually have an old range and a new range that could hold the data. You don't know which one it is, and then you just go random. So there's a tiebreaker there somewhere. So this is just to give you an idea of how much complexity is not in this picture. But it's a lot of fun, and we do the hard work, and if it works, then nobody cares about it. And it does work. OK. So I've already hinted at this. With Raft, like if you go back to this picture, now what we can do is we can look up locations. Like we know which range we have to talk to for which piece of data. And Raft allows us to kind of do atomic writes to that range. So we can basically even group up a bunch of writes which all belong to the same range. We commit them through Raft atomically. So it seems like we're in pretty good shape to building a consistent data store if we're talking to a single range. But in practice, you're not going to be only talking to one range. Maybe you're writing data to this range, and you're also writing data to that range, and that data is related, so you put it in one transaction. You can't do that with only the consensus protocol that we have so far, because you need to do 2 commits, but you have nothing that makes those 2 commits depend on each other. And that's where distributed transactions come in, which are kind of an additional layer on top of this replication. And when you talk about transactions, you talk about ACID, you talk about atomicity, so either everything happens or nothing happens. You talk about consistency, which is essentially, oh, my transaction can't just violate constraints no matter what. The state of the database always stays valid by the stuff that I can do to it. You talk about isolation, which is essentially, for the non-programmers, if there's a box with a donut, with one single donut in the kitchen, and you see 2 of your colleagues racing towards that thing, trying to grab it, when they come back, you know only one person has a donut. You don't find 2 person have a donut, even though there was only one there. Like you can't, if things happen in parallel, they don't behave differently from when they happen in some order. And that's a pretty important one, because like, imagine withdrawing from your bank account from 2 different places, and they both give you money, and you didn't have that much money. That's pretty bad for a bank. And durability is kind of the boring one. Stuff you write essentially stays there, so you should not acknowledge writes that you never wrote to disk, stuff like that. We're going to be talking mostly about atomicity. If you're into isolation levels, CockroachDB supports serializable and snapshot. If you don't know about isolation levels, the one that you always think you use is serializable, and that's also the one that you want to use. Maybe sometimes you want linearizable, but really that is, in very few cases, is that relevant. So serializable is kind of where it's at. And in practice, in a lot, and I dare say most cases, that's what you kind of want, but you don't have it. OK, and now I'm actually going to try to explain how we implement transactions. Oh, no, I'm going to talk about implementing transactions in single node DB first, and then in CockroachDB. So on a single node, you kind of bootstrap off a lower level primitive. So you might want to write a bunch of writes, and you want to make them all or nothing. If you just apply them one at one to your database, that's kind of bad, because if your database crashes in the middle, maybe you've persisted some of it, maybe you've not persisted some of it. You can't persist them all at the same time, because maybe you're touching different files, and there's kind of not a good atomic primitive there. And what most databases do instead, they write everything to write-ahead log, which you can write a single entry to that log atomically, like as supported by the file system. And then at the end, you write a commit entry atomically. And if that entry is there, then it's committed. If it's not there, it's not committed. And because you write that atomically, it's kind of like flipping a switch. And then when it's committed, the database goes and tries to apply all that stuff. If it crashes in the middle, it can go back to that log and kind of restore from there. It's again, extremely simplified, but the takeaway is that this atomic flipping the switch for a commit is the important ingredient. And CockroachDB doesn't have that luxury of being on a single node, so you can't use the file system. But you do have something that gives you an atomic primitive for writing, which is the range, the replication protocol, Raft, that we talked about. So what you can do is you can write to a single key and atomically flip the switch. And we use that in much the same way to bootstrap transactions on CockroachDB. So a transaction has an associated transaction key and a transaction record, which lives somewhere on some specified range, and that range is essentially chosen by the transaction ID. It's not entirely correct, but for all intents and purposes it is. And you commit a transaction atomically. Question? No, you're just like doing the gun. OK. And you commit a transaction atomically by writing from pending to committed or aborted. So that's kind of this flipping the switch that you have in a traditional database when it writes the write-ahead log. And nothing explains this better than a simple illustration. So the way a transactional key-value transaction would go is like you start it. It will write a transaction record which says, hey, I'm pending. You go and you do a write, and that write could be at the other end of the world. This is not on the same machine. It could be anywhere, really. And so you write that value, but you kind of flag it as provisional because you don't know whether it's going to commit yet. And what that looks like in practice, you just write that value, but you put your transaction on there as well. Maybe you do another write. Again, could be anywhere. And now you're ready to commit. And now you use that atomic primitive and go and flip the switch from pending to committed. And now you actually go back to the client and say, hey, I did it. It has succeeded. Everything's good. Now you might wonder, oh, there's still those provisional values out there. But that's fine, because if someone finds them, they're going to be able to look at your transaction record. And you did flip the switch. So there's committed there. And then they know that it's actually real value. But you still go and clean them up after you've acknowledged to the client, because you're a good guy and you don't want to clog the system. You want to save the other people the work of going back to you and checking. So, of course, that's a boring case. The interesting case is when two transactions run into each other. And so if you start at the same scenario, one transaction does one write. Now another transaction comes and tries to read that key, and it sees, oh, there's this provisional value there. I wonder what's up with that. It will actually go to your transaction record, check it. Oh, in this case, it sees it's pending. And because this is a simplified presentation, it will just say, OK, this value is not committed, so it's not there. So I'm just going to pretend it's not there. If you're doing a write where someone else has already tried to write, kind of the same thing. But you see that the other guy is still pending. And now you're like, well, but I kind of want to write there. And so there's some fight in priorities carried out. And if you win, which in this simple example you do for the purpose of illustration, boom, you abort the other guy. And that means this intent, this provisional value that you've seen, you can now freely override it because that transaction has been aborted. Boom. And again, in practice, of course, like what happens if I lose? What's going on there? Then there's a bunch of more complicated situations. But if that made sense to you, then everything else is kind of just complication on top of something easy. OK, so the takeaway is we're doing much the same as a traditional database, except that we have to bootstrap off this Raft consensus atomic commit instead of writing to a write-ahead log. And yeah, I said isolation, the fact that we use multi-version concurrency control and other types of conflict have been completely ignored. But I'm happy to answer questions about them. No, OK. All right, now we're kind of coming back to your question. So what does SQL data actually look like on that transactional key value store? And the primitives for KV, I mean, I've kind of explained that already, but to make it more concrete, the things you can do on a key value store, and you can do all of them inside of a transaction. So you can get a key, you can put a value into a key, and you can conditionally put a value into a key, which is you want to write this value there if the existing value is that thing. And you can scan a sorted key range, and you can delete a key. And the way we store rows, and this is going to change for efficiency, but the way this is set up is still kind of in spirit how we're going to be doing this forever, except that we're going to be grouping more things together. So all tables have a primary key. There's one key value pair per column, and the key anatomy is that you have an ID for the table, then you have an ID for the index, then you have an encoded key, could be multiple keys too, and then you store a column. Okay, and we're going to do examples because this doesn't make sense to anyone, I'm sure. So we're going to have a simple table which has an ID integer primary key. You have a name, which is just like a string, and a float, which is the price of the object. And so into this table, we're going to insert just one silly value, ID 1. The name is ball, and the price is 222. I guess it's a good price for a ball, depending on what ball it is. In any case, so that will put the following values into our key value store. Like both of them start with test, which is the name of the table. Then there's the encoded index, which in this case it's named primary because it's a primary index. The actual keys, of course, they use some ID, so we don't put weird strings and slashes there, but this is for illustration. Then comes the primary key. There's only a single field, a column in that primary key, and it's the ID, so there's a 1. And then we have one row for each column, yeah. One name, one price, and the value is ball and 222 respectively. If we insert another boring column, we get the same thing except that the primary key is now 2, which is repeated twice because we have 2 columns, and we store glove and 333 in there. Okay, so this is that's not magic, right? This is what probably all of us would do if we just came up with a scheme. And as far as the key value store is concerned, everything's just a byte string. It doesn't have a type, no intrinsic information. So what we actually do is all of these are encoded using a really cool encoding which preserves ordering. So it's a pretty nice one. So what do unique and non-unique indexes look like? It's not super exciting. A unique index looks much like the primary key, except that you don't store the columns, but you only store one row for each thing that you're referencing, and the value is the actual primary key, so you can actually look it up. More generally, you want to store all the components of the primary key which are not already encoded, not already covered by the index. So if you have that same table and you have a unique index on the name of the object and you insert the ball into the original table, then the index entry which would be written is the name of the table, test, then the name of the index bar, and then the thing that the index covers, which in this case is only the ball, and the value is going to be point at the primary key. So you get test bar ball pointing to 1, you get test bar glove pointing to 2. And so why is that index unique? Well, if you insert a third thing that has the same name, then the key that it's trying to write is the same as one that already exists, because now you have 2 gloves in your system. And for that write, we use, because it's a unique index, we use one of those conditional puts. So it's a put that only succeeds under the condition that the value that exists is empty. So when you try to insert another glove with a new ID and price, it will barf on you because test bar glove already exists. So that's how a unique index works. And a non-unique index, well, you don't need a lot of fantasy. You just move the primary key to the end of the string to basically allow duplicates that way. So instead of storing the primary key in the value, you move it into the key. So now you have test foo ball 1. If you insert a glove with 2, you get test foo glove 2. And if you insert another glove, it's going to have a different primary key. In the example, it's 3. And that is not the same key anymore as before. So problem solved, you have non-unique indexes. And that is really at the heart of all this stuff. Like the encoding, you can make it more efficient. You can try to collocate more things, because now because things with a similar prefix, they get put closer to each other. You don't want to have like this one index here and this other index there. Maybe you even want to nest the primary key and some of the secondary indexes, so you can actually look them up in one go. That will lead you to something called interleaved tables, which we're also going to have to implement because that is very reasonable. Google Spanner has done it for a while. But yeah, this mapping is not very complicated. It's just a lot of bookkeeping and making sure that you don't fire off too many RPCs. And deployment, well...
We have a question, by the way.
Oh, I do. Perfect. Thank you. How does a distributed transaction implementation differ for Cockroach versus something for analytics? Ryan, what is the question?
You said you guys are doing, like, there's a lot of distributed analytics things like Redshift,
Yeah.
Dremel.
Mm-hmm.
Is that the thing that you guys implement, or you just say there's past few slides that everything you guys have to do? That's the thing that really distinguishes Cockroach?
Sorry.
So you had a few slides talking about how you do transactions.
Uh-huh.
That's something that other people haven't had to do in the past.
Right.
For the analytics thing, that's the real unique.
Well, I believe that no other database does optimistic concurrency in that way. A lot of systems shy away. So to explain, like optimistic concurrency means that your concurrency model is built on the assumption that in most cases you will not have a conflict. So you just do your thing, and then if you do have a conflict, you have to figure it out, because if you don't figure it out, there's something wrong. But if you do have a conflict or a potential conflict, you're going to have to do something about it. And so that is what Cockroach does. Like your transaction will try to run. If there's a lot of contention on some keys, some of the transactions will have to restart. So restarting is kind of the mechanism by which Cockroach solves these problems. One, to give the other guy more time to finish, and B, to have a transaction get stronger with each retry so that it will eventually succeed. Other systems do different things. Like Spanner, for instance, uses locking because they have all this internal Google infrastructure. They can actually do that. Distributed locking, of course, is like a horrible problem to solve, so we don't really want this. And we also have the experience that in a lot of real-world workloads, you don't have that much contention. And it's better to optimize for the case in which you don't have contention to make sure that it's not completely shitty if you do have it. With Postgres and maybe also MySQL, there's also WS replication, which kind of puts buffers all the stuff that's going on in the transaction and just kind of distributes them that way. That works too, but that is kind of hard if you have multiple shards that you need to coordinate. So I don't have a comprehensive survey in my head, but I believe a lot of systems kind of shy away from this optimistic concurrency model. And a lot of systems are also limited in what transactions they support. So a lot of times you can't cross shards and stuff like that because they actually didn't put in that work on top of Raft that we did to bootstrap this thing. Yeah, but in practice, you're going to have to look at all of them. I mean, even Cassandra has something that they call transactions. I would object to that name, but yeah. Okay. So deployment-wise, like we have no external dependencies, and each node is kind of symmetric. I mentioned that we have like this kind of special thing about the first range. That is still like you don't know about that. That lives on somewhere in the cluster. It moves around like any other range. So you have some nodes which are worse if they go down than others, but you don't really know about that stuff, and that stuff moves around like anything else. So from a user perspective, all nodes are the same. There's only one Cockroach process that you run. There's no weird command line flags that you pass to only some of them. And the system is also auto-balancing and self-healing. Like if someone here uses Cassandra and then you know about the ordered partitioner, which is great because it actually does almost all of that work. It puts things in order, so it works a lot like that, like what we're doing, but it doesn't automatically shard those things. So if you have the ordered partitioner, you basically have to decide where to split, and if that changes, you're going to have to reshard manually. So you always have to kind of figure out where your data is, and you have to like figure out the breakpoints. Cockroach does all of this automatically and will also replicate, move data around automatically based on the load. And it's also self-healing. And that symmetry also means like your client can talk to any of the nodes. Like you don't have to figure out which node you want to talk to. You probably just want to use one that's very close to you because that's low latency. So if you read something and that node doesn't have it, it's going to talk to someone who does. So requests are routed internally. And if you add a new node to it, well, we have this gossip network. The cluster is going to figure it out. And so nodes which have data will actually see this new guy and be like, hey, why don't you take some of this data? Because apparently you don't have any. So some of the data is going to move off to that new guy, and you're going to have parity essentially without you doing anything. And similarly, if you have a bunch of happy nodes and then one catches on fire, the other guys are going to figure it out after some point. And remember that you usually have 3 copies of your data. So presumably for each piece of data, there's still 2 copies out there. So they will figure out that they actually would like to have 1 copy more, and so they will add that capacity on another node, which essentially means that you're going to have some interchanging copying of data going on in that cluster. So this is it for the technical stuff, the quick update on the status. We're in beta, and I would like to think that we're in that lower row, so we're not trying to build that car, and it's really sucky until we have it. It's more like, I think it's a bicycle now. Like we don't have distributed joins. Co-locating like data is still a bit tricky. Like if you have a bunch of weird indexes all over the place, you've seen the scheme by which we write to the key value store, so not everything is interleaved as efficiently as it could be. Analytics is not going to work well because there's no distributed SQL layer, but it's pretty useful. I think it's like as useful as like City Bike in New York. Like I use it all the time. It's pretty cool, but I wouldn't want to, I don't know, go to Coney Island with it. And hopefully end of the year we're going to be like the motorcycle and then the cool race car. Though in New York I would argue that having a car is pretty bad. All right, status beta, ready for testing. So obviously we want you to play around with this. I wouldn't put it into production yet simply because we're working on stability. But what's been really instructive for us is just discussing like the schema people are running and kind of the workloads people expect. So hopefully I can grab some of you and see if there's anything here that we could play around with. Roadmap, stability, a lot of stability work. Performance, all across the bank, like going from very low level stuff, but also just making the higher level SQL things less stupid. And then on the side, we have this big push to build a distributed SQL layer. It's all been spec'd out, and like the commits are coming in to build all this distributed framework that will actually like fan out your stuff and aggregate at the source and bring it back in. And yeah, we don't have joins at the moment, but those will also come because they're cool and required. All right, that's all I have. Thanks for the questions. It's been a lot of fun. And there's another question. Oh, Citus. Yeah, I need to look in that more. Will you be able to load the range efficiently if they are contiguous on this? Matthew, CEO. What is the question?
So if we don't really care about looking at like key value, like if we are fine with random keys, can we just directly access what's contiguous on disk? Because for example, when we're training our models, we actually want random order.
So wait, what would it look like? I'm still.
So when we write, it's nice to have a database so we can access single images, for example. But when we're training, we don't actually care about the order.
Okay.
We want to go through it random.
Oh, I see.
And it's much more efficient to load from spinning disks, for example,
right.
as a contiguous block, like the 64 meg block.
Okay.
We can load that.
Oh, so you're essentially saying you want to pull out the whole range at once.
Yeah.
I mean, internally we use range scans whenever we can because that's also like for the same reason it's the most efficient way to do it. So if you are, you would have to just send that query that uses the index, which has that, probably uses the primary index, and just make up the primary index so that it's not sorted, or maybe you sort it by something that you need sometimes, and then that would actually hit the whole 64 megs and pull that out. So I'm not sure. Maybe I'm not understanding.
So you would just do like a select.
Yeah, select star. That's really what does exactly that.
Okay.
Yeah, and it does it better with distributed SQL, because if you don't care about the ordering, maybe it's going to do 10 of those in parallel. If it thinks you need the ordering, then it's going to do them one by one, because that's the order that you wanted.
Yeah.
So if you do select star, like even if it's a primary key, if you don't tell us to order it, like that's something we'll happily break to give you the data faster. Yeah.
Cool.
Yeah. Okay. Cockroach versus Citus. I looked into Citus, but honestly, I looked into so many of those things that they kind of blur in my head. Citus wasn't it something that built on HBase?
Citus is an extension that does Postgres.
Oh yeah, they had a cool demo, right? They did kind of analytics type things that did kind of map reduce in the background. Yeah, it seems like a cool thing. It's like way more analytics-y than we are at the moment. I don't know. I was impressed by making that work as a Postgres extension, but I don't know how that would actually translate to real-world usage. I don't know how it didn't seem like they do a lot about auto resharding or recovery. It seemed like they're trying to solve more that problem that you have a lot of data and you want to run analytics, which is cool. But I would say that probably all of what they're doing is going to be covered by what we envision the distributed SQL framework to be, because that would do the same things, except that it wouldn't do them as a Postgres extension, but do it in Cockroach natively. But yeah. What does it know about the hardware, networking, disk, and location? Okay, I mentioned briefly before that we have entity groups, so you can assign like certain flags to key ranges and key prefixes. And the idea is that you would use those to tell the nodes about the rack or any attribute really. It could be a geographic zone, it could be a rack, could be a power supply. And the other thing that you can do is you can require certain tags for your replication. So to give an example, if you have 3 data centers like Europe, US, and Russia, just to make it completely horrible, you could have things, you could tell things where they should live based on that attribute. So you would, for that prefix, require, let's say, 3 replicas, and you would require 1 to be in Europe, 1 to be in Russia, and 1 to be in the US. So using basically any attribute, you could enforce what lives where. An attribute could also be spinny disk, right? You could have some nodes which are tagged as SSD, some which are tagged as spinny, and then you could say, oh, I want 2 replicas which are SSD and 1 replica which is spinning, and also this one should be in the EU, and this one needs to be in the US because of privacy, whatnot. This stuff has not been built out fully. Like, it doesn't support like very complex conjunctions of things, but this is, I think, definitely the plan. And as like we move closer to production, those use cases actually crop up. This is what we want to do.
When you do a request from Russia, is it just going to access the replica in Russia?
So currently what we do is that we have one leading replica, which is kind of based on read and write pressure. Currently it's pretty silly. The nodes get like a lease and they renew it like as long as they have read pressure. So if the cluster is dormant and you start reading from Russia, then it's going to elect that local node, and so all reads will be local. If you have a more complicated situation where people are reading from Russia and the US, it's tougher. But well, you know, like you always have like these dream projects that you want to do, and one of our dream projects, A, is doing something like ePaxes or inconsistent replication, and the other thing that we definitely want is quorum reads. So you want to be able to designate more than one replica which can serve reads, which in turn means that the consensus algorithm must include those replicas in any majority, because otherwise you might be serving reads. And since we're doing serializable, there's an additional complexity. The replica which serves all the reads, it actually has to remember all the timestamps that it served reads at, because you must not write under a read, because you would change the result of that. And we haven't quite figured out how that will resolve, but yeah, quorum reads is one of those bigger projects that we eventually want to put in. But first we want to like settle all that basic dust. Yeah. What does it know about the hardware? Postgres features we use, CTEs, select for update. So I think So for now, like we support barely any of those Postgres extensions. So the one that we implemented some stuff. We implemented upserts just recently. We did select for update, which I think is essentially just a no-op because some ORMs like to send it, but it doesn't really map to anything with our underlying concurrency model. So for a lot of those things, we actually have to figure out what they should mean in Cockroach. And I guess that's best done by analyzing the actual use case. So I'm happy to chat about that. Table sample, well, upserts, we got that. Table sample, like I don't even know what that does. But yeah.
A fast way of getting percentage of the total rows.
Oh, I see. Okay, so you would just basically sample like a block. It feels like you probably get that with the right query. Yeah.
Special range.
Yeah. Yeah. Just like.
Star, you say every 100.
Yeah. 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 So bottom line, like we don't support many of those. We try to grow that set as like those use cases crop up, but yeah, I'm pretty like Postgres has like insane surface area by now, and I doubt that we're going to go all the way. How does auto vacuuming work? So you're talking about essentially garbage collection, right? Yeah, it's a big topic, and so there are a bunch of layers. First of all, we use RocksDB as a storage engine, like the thing that actually stores data on disk. So it's a log structured merge tree, so it has its own GC story essentially, right? It runs compactions in the background. They've optimized the hell out of this, so I'm fairly confident that is not going to be the breaking point. But there's a lot of other cruft that assembles, right? You have consensus, which builds a log. Eventually, you want to truncate that log, so that's one thing that we do. Then you have this transaction table, which you need to clear out eventually, but you can't do it too early because if one of those provisional values is still in the system and someone tries to check on you, but it's gone, like what do they do? So there are a lot of things that happen there. Then we have MVCC, so we have all those old key values. And I think that's probably the biggest one that I would think could become a problem in practice right now, because what we do is we have a queue which essentially goes over all the ranges periodically, and it will essentially have to do a full scan, and there's a policy which you set which basically tells you how long to keep key values for, and then it will just kind of cut off there, and it has to do that through the Raft consensus because we want to keep the replicas consistent. So that's one thing we'll have to see how it holds up under like pressure. We're just starting up our first like couple 100 gigabyte nodes and try to get them to actually perform pretty intense GC runs, and then just optimize the hell out of it as you do usually. Yeah, as a side note, we will also support time travel, so you can actually run transactions like up so far in the past as you specify the GC. So if you do like 24 hours, you can actually run like a complete read of your data set in the background at like some fixed timestamp within the last 24 hours. That should be pretty nice for analytics once it's all fleshed out. Why Golang? Like I would do it in Rust, but it wasn't available at the time. And also the lightweight concurrency it's not that much there in Rust. Like I have a hard time picturing how Cockroach would look with Metal.io or something like that. It would feel very complex, I think. So initially, I think the choice for Go was pretty arbitrary. I think their CEO, Spencer Kimball, he started like writing this design document, and he started implementing some of it, and the part that he picked was the gossip network because that seemed like an isolated part of the system and just a nice toy project. Like he was working at Square at the time, and he just wanted to learn Go, so that's what he chose. But on a more practical level, like the experience with Go, like I like to bitch about it every now and then, but it's actually pretty good. Like we get a new guy in, and they can actually read the code. With Rust, they could read the code, but they wouldn't really know that much what's going on. It's very easy to onboard. I like the small surface area, actually. Like a lot of people rant about the lack of features. I don't mind it because discussions are usually very short. It's like, just do this, and it's obvious there are no 10 different things you could do. It's not this insane surface as in C++. And with a lot of, like we use like heavy linting of everything. We have like all the lints essentially, and we're very strict about what flies and what doesn't. And so I think like this lack of ambiguity and this like very small surface has actually been very good. And tooling in general is also not bad. Like you have pprof, you have all the sampling that you want. You have good testing, good benchmarking built in. It works pretty nicely. But we almost use all of Go. Like it feels like we've found like a couple of bugs in the standard library at this point. We make heavy use of CGO, which is the FFI interface. We use it for RocksDB mostly. And once you cross that barrier to C++, everything gets much harder, right? So.
Do people who build databases like pick and choose some other things? Like maybe you want to steal some of the cryptography from Postgres, or
I mean, sure. We've sure stolen from people. Like Spanner is clearly the inspiration for all of this, except that we didn't want to like use the stuff that they use for Spanner. But the end goal is exactly the same. The concept of like having smaller shards and having this bi-level index. There's a lot like everything that we learned about problems that other people had. We definitely did not ignore it. So yeah, it's definitely a long time coming. And also the concurrency model. It's like heavily inspired by some papers. Like notably, I can't remember the other one, but one is a critique of write snapshot isolation by Yabande from like, I don't know, 80 something maybe. So yeah, this is like a confluence of a lot of ideas which have been around for a while, but just we think haven't been put together in that way that everyone can use. And my Golang. All right, I think we got all of them.
A few more questions.
Yes, go for it.
I don't have a computer.
Oh yeah. Well
Can you
then
use SQL?
come again.
Can you use something that is not SQL? to talk to
Not right now, but
Is it planned?
yeah, like really SQL, it's kind of a love-hate relationship, right? It's kind of a lot of surface to implement. It's declarative, so it's pretty tricky to get it performant. Yeah, I don't know that we have explicit plans for this, but there's really nothing that stops us from exposing these things through like a custom RPC protocol. Like internally, we use gRPC, and we weren't SQL from the start. Like the plan was to build a cool transactional key value store, and then it'll be awesome. But then we realized like nobody's going to go out there and build his stuff for a transactional key value store, and SQL was just the sane one to use, and especially. Just jumping on Postgres gave us a pretty efficient wire protocol, and we can actually write client drivers just by a small patch to an existing driver, mainly to get that optimistic concurrency handled better. So yeah, we don't love SQL, but it's just like that's the thing. That's what people use. But there's nothing that stops us from just putting in an RPC-based protocol, for instance, if that is something that makes sense.
Also, what's the recommended data size? Like, can you use this as a file system kind of? Like
We actually have a toy example which implements a fuse file system on top of Cockroach, but it's not a blob store. Like you don't want to use it for big stuff. Like think 64K, 128K, that's probably fine, but this is all stored inside of RocksDB. So RocksDB, I don't think prides themselves on on big stuff. But yeah, we've like tossed around. Like once you have a transactional key value store, you can actually do a lot of things. Like you can build your own S3 pretty easily. And we've actually toyed with that idea of building like a Cockroach S3 type of thing, which internally uses Cockroach to store the metadata and then does something else for the actual big stuff. And so yeah, no blobs in Cockroach, please. At least not at the moment. But in like a far future in which we have a lot of time for this sort of thing, you could actually imagine something that would just make you use it. Like you could just store big blobs in SQL, but it would internally actually do the right thing and not store them in RocksDB and make it completely transparent to you, which would be cool. But
yeah, because you have kind of like some parts of GFS built in.
Right. Right.
GFS
Right. And the other thing, of course, that we could also do is just go on just not do replication at all. But yeah.
Okay.
So yeah.
What about like a query planner?
Come again? A query planner?
Query planner,
Yeah, we have that today, but it's not the smartest one. And just to give you an idea of how hard this is, like I think, I don't know if that's true now, or maybe that's just an urban legend, but apparently at some point at Google, if you had a Spanner query that you needed optimized, you would send it to a mailing list, and they just send you a better query back. So it's hard, but that is kind of, with this distributed SQL push, we're trying to get a decent query planner going, and it would have to use a lot of like circumstantial information, right? It needs to kind of figure out how many things it's going to touch and kind of where those things live, and then kind of go from there. Yeah, it's a huge project. For now, we have one that's reasonable but not great, especially if you're touching multiple things.
So for actually deploying it, is it as simple as like pulling up Kubernetes pods and just?
Well, Kubernetes, yeah. Kubernetes has a problem that it still hasn't figured out its local storage story that greatly yet. Like I think there's talk about maybe running as a daemon set is the right thing. There's like an open issue where someone tried it, and if you want just a toy example, yeah, you can fire up a pod and it looks nice, but it's not the full deployment story. I think is tricky. But even for other databases, I think Cassandra is now like a built-in thing, or they have some add-on for it because you couldn't just set it up without some hackery. We hope that, that Kubernetes figures this out better, and then, yeah, and we certainly do everything to make it really easy. Like, I could, yeah, if you go to a README, it's like a one-line thing. You just start the thing. There's nothing else. So it needs to discover other nodes somehow, so you give it a load balancer or whatever, and then you're essentially set. The local storage is really the thing that's tricky with most things. All right, I think everyone's happy. So I'm going to stick around a little bit and then try to quiz some of you about what's running in-house. And yeah, thanks for the many questions. It's been a lot of fun.